AP Review, Lessons 3 and 4. This review will cover a good number of topics that we discussed in Chapter 4, mainly solubility ideas, including precipitation reactions, and then the quantitative measure of molarity, which is the most common way of expressing concentration. So we began with discussing solubility rules, and this question kind of gets at the idea of solubility. Recall that in general, a few very general rules of solubility are that among the cations, group 1 metal cations are always soluble. Remember, these are the sodium, potassium, rubidium, and so on. Always soluble, no exception. Among the no exceptions are also the ammonium. Ammonium ions are always soluble, no exception. That's usually with cations. Now there's also a lot of group 2 ions that are soluble, but they do have exceptions. So group 2, which are the alkaline earth metals, are soluble, so like magnesium, calcium, but there are exceptions depending what the anion is. So for the most part, group 1 and ammonium are the soluble on the cationic side. On the anionic side, this would be the anions. Very important to remember that nitrates are always soluble. All nitrates without exception are soluble. That all acetates without exception are soluble, so C2H3O2-, chlorates, perchlorates minus are soluble. These were essentially the general rules. Now there was kind of in the middle of the road a guy or a group. Let's see, the halogens from group 17. We said were soluble, except the exceptions are, remember, the silver, the three robbers we call them, the silver, the lead, and the mercury, Hg. The way is 2 plus, and don't be confused, there's a reason why we write the 2 down here. Mercury famously doubles up in the ionic form. So these are the 3 exceptions. The other was the sulfate, and remember the 3 robbers and then the 3 bandits. So here are your 3 robbers again. These are the robbers. Oops. The bandits, remember, were actually these guys right here. These are the 3 bandits. And that's why I mentioned them here as being kind of in the middle. So these are the general rules. Again, you want to remember you're always soluble with group 1, you're always soluble with the nitrates. And then try to hold on to these. So now looking at these compounds, we can right away cross out the nitrate. Here's the nitrate. It's out. It's not soluble. Right away here's potassium. This guy's out. Not soluble. Here we can see chloride. We said the halogens are soluble, except in the case of the 3 robbers, the 3 bandits. Magnesium is not one of the robbers or the bandits, so this one's also soluble. He's out. It's between aluminum sulfate and nickel sulfide. Now, aluminum sulfate, again, has this middle of the road sulfate anion. And because it's not teamed up with one of the robbers or the bandits, this one's always also soluble. So the one that essentially doesn't fit is the nickel sulfide, nickel 2 sulfide. And in fact, that is the one that is not soluble. Usually if there's an anion like sulfide that's not in our rules that we didn't discuss, we'll assume that it's not soluble. Here's a second question really along the same lines. Here we say a student prepares an aqueous solution containing these 5 cations, silver, lead, copper, manganese, and barium. The student observes that no precipitates form in the solution. Which of the following could be the identity of the anion? So the idea of precipitate, remember, is that if we mix 2 soluble solutions, say for example if we mix sodium carbonate, which is aqueous, it's very soluble because of the sodium, And if we mix that with, say, calcium carbonate, which is also aqueous, I'm sorry, not calcium carbonate, calcium chloride. Let's do calcium chloride. Calcium carbonate would be the product, which is always also aqueous. Here we have two precipitates, possible precipitates that can form. The sodium will replace the calcium replaces the sodium, and we get ourselves sodium chloride and calcium carbonate for our products. Sodium chloride is still soluble, so this would be aqueous, but the calcium carbonate actually is not, based on our rules. It is a solid. So this is, recall, what was called a precipitate. And you can predict the production of precipitates based on the compounds that you add together. So here we're saying none of these precipitate, which means we have to find an anion that would match that. Now the only anion that matches it is the one from the previous slide, nitrate, because there are no exceptions to the solubility of nitrates. Every nitrate is soluble, and usually we actually use nitrates to deliver any metal ion to a solution, because we're guaranteeing that it will be soluble. So the rest are bandits and robbers and some things we didn't even talk about, like dichromate here, or I'm sorry, like chromate here. So we'll assume that they are not soluble. How about a question involving molarity? Recall that molarity is moles over liters. It's a good idea to be able to rearrange the equation to solve for moles, which would be molarity times liters, or to solve for liters, which would be moles over molarity. Be able to do this. It's very common for the AP exam to ask for you to do some calculations involving molarity. So a student prepares a solution by dissolving this much in glucose. The molar mass is given, as is usually the case with multiple choice questions, and enough water to make 250 milliliters of solution, and we're asked to find the molarity. So let's go ahead and first get the moles, and we get the moles by dividing grams by molar mass, so 60 over 180. Now, again, you can't use a calculator here, so you have to recognize that 60 goes into 183 times, but we're doing it 60 divided by 180, so really we have a third. In other words, 0.333, repeating. So we have a third of a mole, essentially. And then dividing it by our liters. Now remember, milliliters to liters, you have to divide by 1,000. So we have ourselves actually 0.250 liters, or a quarter of a liter. Now, anytime you divide by a quarter, if you remember, say if you have 2 divided by a quarter, in math, dividing by a fraction is the same thing as multiplying by its reciprocal. So you can do 2 times 4 once. So really it's multiplying by 4. Essentially what we're doing is we're doing 0.333 times 4. And if we recognize that, then 4 times 0.333 is going to be equal to 1.33, because we have a third times 4, so now we have 4 thirds. 3 thirds is 1, and so we have 1 and a third left. A third is 0.33, and that would be the answer. So you want to pick C in this case. Again, some calculations without the use of a calculator. Here's a quick question, not much going on here. This is more of a definition type question. Here it says if 2 moles of KCl are dissolved in water, how many moles of ions will the solution contain? Now, because KCl, as it dissolves, and every ionic substance as it dissolves, dissociates or breaks apart, you could take a look at how many ions are formed. So in this case, because KCl breaks up into 2 ions, you get yourself twice as many ions produced. If you were to dissolve something like calcium chloride, that would actually break up into 3 ions. You would get yourself 2 chlorides. So for every 1, you would get 3. So because KCl is very soluble, you'll actually get 2 moles of ions. I'm sorry, not 2 moles of ions, 4 moles of ions, because we begin with 2. Since we begin with 2, we'll get 4 moles of ions. Now, when you'll get between 2 and 4 is when you have a substance that doesn't dissociate, like a weak acid or base. and then we'll talk about these as we get to them, we'll review them, but that's when you would get between 2 and 4 moles. And finishing up with this question, actually we have this one and one more question. The volume of water that must be added in order to dilute 40 mils of a 9 molar HCl solution to a concentration of 6 molarity is closest to blank. So what we're doing here is doing a little dilution problem. Now we gave you a dilution equation which you can use, or you can use molarity, because molarity is enough to be able to solve this. The dilution equation, remember, was M1V1 equals M2V2. So we got a 9 molar solution and 40 milliliters of it, so your molarity is 9.0 times 40, and we're going to get it down to 6 molar, 6.0, put 0.0 in there, times some unknown quantity. That's what we're trying to solve for. So if you rearrange this, 9 times 4 is 36, but because it's 9 times 40, we got 360 on this side. Then we're going to divide by 60 to solve for x. Notice what I did, I just divided that down here. So 360 divided by 60, that's like 36 divided by 6, which gives me 6. I'm sorry, not 60 here, this was a 6.0. So this would give me, x would be 60 in other words. Apologize for that mess a little bit, but if you can quickly do this calculation, again, you can't use a calculator, so you would have to do this sort of thing. So 60 would be how much volume we would have in the end, the final volume. Here, however, it says how much must be added. V2, remember, is the final volume. In fact, we oftentimes said it MFVF for final. And we did MIVI for initial. So this is the final volume, which means we have to add 20 milliliters because we began with 40 mils, so we have to add 20 milliliters to get us to 60, and that would be the answer. Another way of looking at this, if you want, you can actually logically see it. We're going from a molarity of 9 down to a molarity of 6, so we're decreasing the molarity by 2/3. In other words, 9 times 2/3 will give us 6.0. If you can kind of see that, because 6 is 2/3 of 9, which means our volume must increase by that much. Our volume must increase by 3 seconds. So we begin with 40 mils. 40 times 3 is 120 divided by 2. That's how we get our 60 milliliters, as we did before, as we did here. And then you realize that you have to add, so you're back down to 20 mils. That would be an alternate way of solving the problem. Again, look through this problem, make sense of it, be able to do both a dilution problem and be able to do a molarity problem like the previous one. Let's finish up with number 6 here, and this is a problem that's a little more involved. It's still a multiple choice problem, but this one gives us some diagrams and something to explain. So we have a few beakers X and Y. Here's X, here's Y, each containing a solution, 1 liter solution. So this is 1.0 liters and 1.0 liters. A student combines the two solutions by pouring them into a larger beaker, this beaker here, and observes the formation of white precipitate. Assuming that the volumes are additive, which of the following sets of solutions could be represented by the diagram? So just by looking, you can probably see that we got ourselves, in the left side, we got the silver nitrate. So this guy right here, the big molecule, is your nitrate, because you've got four atoms there, and your pluses are your silvers. Your silver is your plus. In this case, chloride is the minus, and your double pluses, they're a little hard to see, are the magnesium, because magnesium is in a 2+ charge. What you see in the final beaker is you see that you have both nitrates and you have magnesium. You don't have any 2+. You don't have any chlorides left, nor do you have any silver left. So what we'll assume is that all of the chloride got used up and all of the silver got used up. This will allow us to predict which of these two are possible. In other words, since we don't have any chloride, all the chloride must be used up. Now here we have 2 molars, two molar solutions all the way down, which means in a 2 molar solution you have 2 moles of Ag+, and you have 2 moles of nitrate minus. In the top case here, we have, remember, for magnesium chloride, for every 1 mole of magnesium you get 2 moles of chloride. So you have 2 moles for the top one here of magnesium, and you actually have 4 moles of chloride. So we have to, but the picture shows that we have no chloride left, no Cl- left in the solution, which means all of the chloride must have been used up. If we were to have 4 chlorides, then as it precipitates with the silver, notice these will precipitate. The silver precipitates in a 1-to-1 ratio with chloride. As it precipitates, we'll have some chloride left over. So these, in other words, cannot be the possibilities. We have to end up with a 1 molar. We have to begin with 1 molar solution. So it's going to be one of these two. So we were able to reduce the choices down. So run that back and think through it again to see if you understand why. Furthermore, now because these are the same, it all comes down to beaker Z. Now, if you take a look, since we had twice as much chloride as we had magnesium, what happened as they precipitated is that the chlorides went with the silver and the nitrates went with the magnesium, and you ended up essentially at the end with magnesium nitrate, which has twice as much magnesium, twice as much nitrate for every magnesium, and that's why it's a 2-to-1 ratio here. But the question is whether it's a 1 molar solution that comes out or a half a molar solution that comes out. And because we began with 2 moles of nitrate, here they are. Put this in a different color. We have 2 moles of nitrate, and we began with a mole of magnesium. In other words, we decided the real solution was 1 magnesium and 2 chlorides. What we've got is we've got this in the solution essentially. In other words, we've got 1 moles of magnesium and 2 moles of nitrate, which come back. So in other words, we have 1 mole of magnesium and 2 moles of nitrate, which combine together essentially into this guy right here. So 1 molar would be our when we combine the two. However, the answer is actually 0.50, not 1.0. And because we've mixed 2 liters, remember we had a liter of each, 1 liter of this, 1 liter of this, so they in effect diluted each other. So we had 1 mole of each, and we divided by 2 liters, and that's how we got ourselves half molarity. So D would actually be the answer here. Now this is a little involved, so think through it. Actually, what I would recommend is erasing it and thinking through the problem yourself. Okay, so this concludes for us Lesson 3 of the AP Review.